Okay, time for our last video, our last topic, not just the last video in this video set, the last topic of the entire course. Hooray, this is it. And so what's this video about? Finding nth roots of complex numbers. What's going on here? What do I mean by this? Well, let's start talking about square roots. So if we want to think about square roots of a number like 9 here, think about numbers such that when you square them, you get 9. So 3 is a square root of 9, because if you square 3, you get 9. -3 is also a square root of 9, because if you square -3, you get 9. So we can see there are 2 square roots of 9, 3, and -3. So we could think about not just square roots, but we could think about cube roots, or we could think about fourth roots or fifth roots. And so in general, we want to think about, the nth roots of a complex number W are numbers such that, let me maybe say solutions to the equation z to the n is equal to W. And in general, there are nth roots of a complex number. So there are 2 square roots in general. There's 2 square roots of 9, 3 and -3. If I ask you about fourth roots, we should expect there to be 4 fourth roots. If I were ask you about 17th roots, we should expect there to be 17th roots. As an example of this, that there are 4 fourth roots of 16. And let me just list them off for you. 2 and -2 and 2i and -2i. Let's check that each one of these is a fourth root of 16 just by raising it to the 4th power. So 2 to the 4th is 16. Now I do -2 to the 4th, check for yourself that yes, you get 16 as well. 2i to the 4th, we can write that as 2 to the 4th times I to the 4th. I to the 4th is 1, so this is just 16. And -2i to the 4th, -2 to the 4th, I to the 4th, again, I to the 4th is 1, so this is 16. So hooray, these are the 4 fourth roots of 16. What's the leftover question here? How to find them. So if I give you a complex number W and I say find the 3rd roots, the 4th roots, the 5th roots, the 6th roots, whatever there, how do you go about finding them? That's going to be the point of the rest of this video. So our running example is going to be find the 5 fifth roots of W is equal to 1 plus I. So alternatively and equivalently, I can say find solutions to z to the 5th is equal to 1 plus I. These 2 formulations of the problem are exactly interchangeable. So how do we go about doing this? I'm going to be a couple-step process. Here's going to be my procedure, my mechanism for doing this. So step 1 is going to be find a single solution to z to the 5th is equal to 1 plus I. Find a single root of it. So there will be 4 that we won't find, but find one of them using exponential form. So what do I mean by this? So If W is equal to 1 plus I, check for yourself that R is equal to square root 2 and theta is equal to pi over 4, or I don't think you even have to check for yourself because I think we did this in the previous video. So this tells us from this, we get that W is equal to square root 2. Let me write, instead of square root 2, I'm going to write 2 to the 1/2 e to the I pi over 4. So then Z, we're going to literally just write W to the 1/5 power. We're just going to take the 5th root of everything in sight. 2 to the 1/2 e to the I pi over 4 to the 1/5 power is going to be 2 to the 1/2 raised to the 1/5 power e to the I pi over 4 raised to the 1/5 power. And we end up with 2 to the 1/2, all that to the 1/5 power is 2 to the 1/10. E to the I pi over 4, all that to the 1/5 power. Multiply the exponents together again, e to the I pi over 20. So 1 root is going to be Z is equal to 2 to the 1/10 e to the I pi over 20. Okay, so we found, this is the first step. We found 1 root here. One of the solutions, at this point, we found one solution to Z to the 5th is equal to 1 plus I. If we want to check, we can do this quite easily with the Demas formula from the last video. So Z to the 5th is just going to be 2 to the 1/10 to the 5th e to the I pi over 20 times 5. Sure enough, you get 2 to the 1/2 e to the I pi over 4. And we said, from the previous slide, that is 1 plus I where we started. So great, we found 1 root here. Okay, we need to find the other roots. How do we do that? Step 2 is find the remaining roots. In this case, we have 4 more remaining roots by adding integer multiples of 2 pi over 5, or I would say in general, 2 pi over n to the theta from the first root. So the theta from our first root here is pi over 20. And so how do we find the remaining 4 roots? We're going to add integer multiples of 2 pi over 5. That 5 down here, this is coming from, we're looking at 5th roots. If I was asking you to find 6 roots, you'd be doing 2 pi over 6. So I was asking you to find 7th roots, you'd be doing adding integer multiples of 2 pi over 7, so on and so forth. So let me make a list of our roots here. So I'll call them Z1 to Z5. Z1 is just going to be 2 to the 1/10 e to the I pi over 20. Z2, so all of them, we're not changing the R. We're just going to add integer multiples of 2 pi over 5 onto the theta. So Z3 will be 2 to the 1/10 e to the I pi over 20 plus, so 2 times 2 pi over 5 will be 4 pi over 5. Z sub 4 will be 2 to the 1/10 e to the I pi over 20 plus, this one will be 6 pi over 5 will be our next multiple. And Z sub 5 will be 2 to the 1/10 e to the I pi over 20 plus 8 pi over 5. And so we are done here. These are the 5 5th roots 1 plus I. These numbers are the 5 numbers that satisfy z to the 5th is equal to 1 plus I. Okay, so in some sense, we're done. There's a couple of things I want to do here. So number one, why do we stop at 5? Let me just point out here that if we were to decide to add on another multiple of 2 pi over 5 here and keep the pattern going, z sub 6 is 2 to the 1/10 e to the I pi over 20 plus, now there'd be a 10 pi over 5, but 10 pi over 5 is really just 2 pi, and e to the I pi over 20 times e to the 2 pi I, we know from a previous video, that's just 1, and this is just back to z sub 1. So we start just looping around. So loops around. So we should not do this. Second thing to do is just check that these are all, these are in fact solutions to z to the 5th is equal to 1 plus I. Let me do this for z sub 3, try it for yourself on z2, z4, z5, that if we raise z3 to the 5th, that would be 2 to the 10, 2 to the 1 over 10. Let me make that a little bit nicer. To the 5th, e to the I pi over 20 plus 4 pi over 5. And then we would multiply this by 5, and we would get 2 to the 1/10 times 5 is 2 to the 1/2. E to the I, so pi over 20 times 5 is pi over 4, plus 4 pi over 5 times 5 would just be plus 4 pi. And yeah, we see the same thing here, 2 to the 1/2 e to the I pi over 4 times e to the 4 pi I, and e to the 4 pi I, this is also equal to 1. Like, by Euler's formula, check that for yourself if you don't believe that. And yeah, we are right back to 1 plus I, where we started. Okay, so that's the second thing to check. The third thing to check, the third thing that I want to do is to show that there's actually a really cool graphical representation of this. The picture here is really pretty, so I want to show it to you. And so I want to plot these points here in the XY planes. And so we want to convert this to their X and their Y coordinates. So if we have z1 is 2 to the 1/10 e to the I pi over 20, this would be, so the X coordinate would be 2 to the 1/10 cosine of pi over 20. The Y coordinate would be 2 to the 1/10 sine of pi over 20, writing this, as x comma y. This one would be 2 to the 1/10 times cosine of pi over 20 plus 2 pi over 5. This would be 2 to the 1/10 sine of pi over 20 plus 2 pi over 5, and so on and so forth. So what I want to do is I want to switch over to Desmos to finish things off here. So I've already have pre-made here. So this is the, right here, this is the first point. I guess I can give it a label of Z1 is our first point here. For all of the later ones, let me just kind of copy paste here. The only thing that's going to change is that I'm going to add multiples of 2 pi over 5 to the arguments of the sine and cosine. And so here is our second point here. There is z sub 2. And okay, let me copy paste down here that this one is going to be, we're going to change this to 4 pi over 5. And that one is going to be Z3. And so maybe you can kind of see here, is there a pattern? Is there a nice picture that we're making here? And the answer is you betcha. Yes, is there going to be a nice picture? Here's Z sub 4. And finally, Z sub 5. I get all of those changed there. And so what do we form here? These 5 points form a nice regular pentagon. The 5 fifth roots of this number 1 plus I are going to form a nice pentagon that's centered at the origin. And there's nothing in particular here about the 1 plus I. You know, pick any complex number to do the nth roots of that, and the nth roots are going to form a regular n-gon. You want to do the 6 roots of unity are going to form a nice hexagon, a 6-sided figure. The 7th roots of your number are going to form a nice, you know, septagon or heptagon or whatever words you want to use there for a 7-gon. And the last thing that's pretty cool here is that all of these points have the same R value, 2 to the 1/10. And so they're all going to fall on the line that has equation x squared plus y squared is equal to 2 to the 1/10. All of that squared. Take a look at that. So if I plot the circle x squared plus y squared is 2 to the 1/10 squared, or just 2 to the, you know, let me make it a little bit more elegant looking there, 2 to the 1/5. All 5 of the points fall on that. So we have this very nice, pretty picture that they're all equally spaced around our circle. And from this, we can see that, like, again, the Z6 would be coming back here. Z sub 7, we kept going around. We're just going 2 pi over 5 radians around the circle each time. Okay. Well, that finishes off this video, and that finishes off the class. Hope you enjoyed these videos.